Welcome to Innovate and React. I'm Kevin Hares, and in today's episode we will talk about innovative hydrogen storage solution. Today's guest is Jonas Massa, co-founder of AKROS Energy, and they are developing new solutions for hydrogen storage and transportation. Hi, Jonas.
Hi Kevin.
Yeah, thank you for being here and talking to me about your new solutions on hydrogen storage. But maybe first, what brought you to hydrogen?
Yeah, I'm a chemical engineer, and in my study, I focusing on chemical hydrogen storage. Yeah, I studied in Bavaria in the FAU, and there the whole topic of hydrogen storage within LOHC is a big topic. And there I moved in with my master thesis and started a study about the refueling station that is autonomous with LOHC. And then I directly go in the whole field of hydrogen storage. And after my switch to my home location near Rostock, I started at the H2 Apex company. And there was also a focus to hydrogen and how we get hydrogen as a molecule sufficiently stored in a media that is non-hazardous and so on. And therefore, I started to go on with research regarding hydrogen storage.
Maybe for those who are not familiar with the abbreviation, the LOHC, what is that again?
Yeah, LOHC is a type of liquid organic hydrogen carrier, right? This is a type of molecule, namely dibenzyltoluol, was able to store hydrogen within the organic structure of a molecule. And there we are able to store hydrogen in and out of the heated oil, I would say.
Well, basically store it as a liquid. And that's also what the problem is that we want to discuss today. When we are looking at hydrogen, we have the electrolyzer technology to produce hydrogen that's already known for a long time. And we have a lot of processes in the chemical industry that use hydrogen already, mostly gray hydrogen nowadays. But ideally, we want to replace that. And the production sites are not necessarily where the use of the hydrogen will take place. So we need ways to transport the hydrogen and store the hydrogen. So what is the main problem in your opinion with this storage and transportation of hydrogen?
Yeah, as you said, we have the problem with renewables that they are not well distributed in location and not well distributed in time. So we have also fluctuation within a time period, a short time period, day to night, or a long time period of seasonal effects. And these are the two obstacles of renewable energies, and therefore we need hydrogen to store energy and make the energy reliable at any time and anywhere. And there our system comes into play, how you get the molecule hydrogen itself stored, because hydrogen itself, it's a green molecule. When you burn it, it only evolves water and no CO2, but nevertheless hydrogen is an explosive gas or a flammable gas, and therefore it's an obstacle in regard to acceptance of the society and in regulation and in hazardous potential.
And then it comes also into new places, because when we now have the current fossil-based system, we have the hydrogen production as the big methane reformers in a chemical site. It's very confined and there are not a lot of untrained people anywhere near. And if we go to this green hydrogen, we can think more of decentralized solutions, small wind farm or solar panels, and then can also be produced somewhere else, right?
Right. And this is a big point, because when we decentralize, as you said, we will include personnel that is not well trained in industrial processes and so on. So we need a carrier or something like that that is easy to handle in a wide spectra of personnel or of humans that interfere with the technology.
Yeah, exactly. You already mentioned the LOHCs, which is a solution for this problem. What are other state-of-the-art storage and transportation solutions that we have?
Yeah. The most advanced or the most used hydrogen storage is a pressure vessel.
Yeah.
So the normal way is to pressurize hydrogen up to 700 bars, especially in refueling fuel cells or fuel cell buses or something like that. Here I'm located in Güstrow. We have a fleet of hydrogen running fuel cell buses. So
Interesting.
it's the common way to pressurize hydrogen to use it in mobility. And moreover, we used ammonia as one of the biggest chemical feedstocks to store hydrogen. And ammonia has a problem. It's toxic, and therefore, when we want to spread it in the wide application, we have the problem of toxicity in handling these chemicals.
Yeah, definitely. It might be a solution for these like chemical companies. It's already traded as a commodity for fertilizer production. But if we're thinking about more like people's homes or cars, then that's not an option.
Right. So yeah, there we have to differentiate the different application of hydrogen. Yeah. Every application have its own unique criteria. Yeah. Maybe in regard to toxicity, handling, or energy density, or how cheap it should be, something like that. So we have a lot of criteria that change when we look to different sectors. Yeah, especially in mobility, it's important that we have a high energy density. Because our car has to run a long way to the next travel point where I want to go. But when we're looking to stationary hydrogen storage or stationary energy storage, energy density is not that important in regard to other criteria like efficiency. I want to have an efficient system that is able to store seasonal power efficient. And there you see in different application, we have totally different criteria, and therefore other technology will appeal to different niches. And especially ammonia has a high energy density, but the efficiency is not so great. But a high energy density is cool when we want to transport it worldwide over a big distance. And then ammonia comes into play from
ships,
harbor to harbor with industrial facilities. But when we go to the inland sector, ammonia will have some obstacles in regard to toxicity.
Also, can you easily transport it with trains, for example?
Yeah, it's able to transport with trains, but there the regulation will fight against you.
Okay.
Yeah, it's hard to get a new energy carrier within the regularity framework. So we have to consider this when we want to speed up in the whole renewable energy sector. We have to find technologies that are easy to scale up and easy to get in permission.
Yeah, I think that brings us also to your technology. How are you with AKROS Energy tackling this problem?
Yeah, we store hydrogen in salts. So we use two different salts, namely potassium bicarbonate and potassium formate, and they are really used by industry. Yeah, so potassium bicarbonate is used for anti-flaming agent or baking soda in your kitchen, and we have a process that is able to store hydrogen on that baking soda and produce potassium formate. And potassium formate is also a salt that is non-toxic, that is used for anti-icing agent for airplanes in the winter, or deep sea drilling of oil. So to seal the drilling hole, they used potassium formate because it's environmental friendly.
Okay, so it's actually so environmental friendly that you can put it on the borehole and then it might get into the sea or whatever, but it's not toxic to the fish or anything.
Right.
Interesting. And also baking soda, I think that speaks for itself how untoxic it is.
Yeah, and that is the coolest thing in chemistry, when you can handle such non-toxic materials in your lab. It's without any fear or something like that. We can taste the different salts. Yeah, you will figure out a different taste when the hydrogen solution is loaded with hydrogen or discharged. You can taste it.
Really?
Like in the older days of chemistry, where always you try to taste something. Yeah.
These chemicals are known for a long time, and what brought you the idea to use this as a hydrogen storage medium?
Yeah, the idea is not originally from us. Since the 80s, there was research about the system, and in Israel they found out that it's easy to store hydrogen within this salt system. And we developed a process that is able to scale it up to a bigger scale or to a market entry level. Because from that on, it was only in lab scale with a small amount of catalyst and a small amount of ingredients, and we developed a process that is able to scale fast to move it in the market.
Yeah, that it can actually be used in large scales, because when we are talking about this kind of energy storage, we're not talking about grams. It's more like several thousand tons that have to be used at some point.
Right. When we looking to different application, for decentralized application, there will be smaller plants. But when we're looking to global transport, we're talking about gigawatts of hydrogen that are stored and released in the harbor for a sufficient energy transition. Therefore, we have different scales, and we as a startup, starting with a small scale, and from that on, building bigger and bigger plants to fulfill the demands of the future.
And your technology is the catalyst, which makes this reaction possible. And I assume the catalyst is then inside of a reactor. Maybe talk me a bit through your process. How does it start from the hydrogen? And
yeah, for sure. So we have a cooperation with the Leibniz Institute for Catalysis. So since years we're working together, and we start invention in the field of the catalyst. So we have a heterogeneous catalyst that is fixed in the reactor. So it's a fixed bed reactor, and it's a way easy process. Yeah, we have our salt solution. So we take the salt, put it in solution, then we have basically salt water, and our system is the second unique selling point, that we have a low reaction enthalpy. Therefore, we need only a temperature of 60 degrees. So we heat the solution up to 60 degrees, and then we put it in the reactor with the catalyst, and immediately the hydrogen is evolving from the salt water and is flowing outside of the head of the reactor.
So that's the decoupling of the hydrogen. And how do you load your salt with hydrogen?
Yeah, that takes place in the same reactor. So we cool the whole system, because the chemical equilibrium itself, it's near ambient conditions. So when we want to store it, we pressurize the whole system up to 10 to 30 bars, and then we bubbling in the hydrogen, and then directly, due to the same catalyst, the hydrogen is stored in the solution. So we used one reactor to fulfill both.
Great. That makes it way easier.
And cost efficient. And cost efficient, because at the end, hydrogen will be a commodity. Therefore, we need a process that is easy to scale with lowest cost. Yeah, we basically have a pipe with our catalyst, and we have a pump and a heater, and that is how the magic works.
And you don't even need that big of temperature changes. That's also great. When you think about Haber Bosch at like 200 bar, 300 degrees, that's a lot of energy that is also required for just the reaction conditions.
Right. And when we're looking to decentralized application, we will not have that high temperature range. Yeah. When we're looking to a village, we might have some combustion engine for burning hydrogen to re-electrify it, but then you have excess heat about 100 degrees or something like that, but not 300 degrees. So when we look to decentralized application, we will not have that excess of heat at the location in contrast to a harbor or a chemical plant. When you're looking to BASF or something like that, you will have some processes that will have exhaust heat at certain temperature, but not in decentralized application.
Yeah, exactly. There you can rely on other processes, but if you have to produce the temperature just for the process, then it's more complicated. Your process can then be used to have a hydrogen, like an electrolyzer, for example, and then just also dynamically use up what the electrolyzer produces, or does it have to be a continuous flow of hydrogen?
Yeah, as a chemical engineer, I like a continuous flow of streams.
Yeah, that's the easiest.
But in general, there we have also combined different technology because we need a pressure tank to buffer the fluctuation of electrolyzer. Yeah, when we want to use our chemical process to buffer this fluctuation, we need to have a bigger reactor, and therefore we are not cost efficient. When we have only a small buffer tank, we combine the advantages of this system and couple it with our system. So we have a small buffer tank that is able to get the fluctuation, and from that on, we have the connection with our chemical process to balance these fluctuations.
Interesting. So you need also a gas storage, but you can have that much smaller because you use then your salt or salt water as the actual storage. And then when you want to produce something from it, you can use the same reactor to convert it back. Or would you have in that case two reactors of the same kind? They just serve a different purpose, but the catalyst is the same?
Yeah, we have two different areas. The first one is stationary application. There we will have only one reactor to fulfill both reaction. And the second way is the transport sector. Yeah, there you imagine an area with a lot of renewables, maybe Middle East or something like that. And there you put only a plant that is able to store hydrogen within the salts. Therefore, you need only the hydrogenation process. And only a catalyst that is specifically improved to handle this. And then you ship the salts to a location where the demand is higher, maybe Germany, and there you need only a plant that is able to produce the hydrogen out of the salts or release it. And then you have only there the dehydrogenation step.
Yeah, I think when it comes, because one of the processes needs to be heated, the other one needs to be cooled, it's easier to, or not easier, it's more efficient to have it really dialed in on these conditions. If you want just to produce the salt on one place and then convert it back on the other place, then you don't need on the production side where you have to cool it, right? Then you don't really need the heating part.
Yeah, right. But the cooling on the other side, it's so low because we use water, and that is only tempered slightly and then came out with a temperature of 40 degrees or something like that. So that is not the biggest part to cool it down.
Okay, then that makes the whole process really lean, I guess. You don't need a lot of fans or stuff like that.
Yeah, and you also can imagine two different states of matter. Yeah, the one is the solid salt itself, and the second one is the salt within solution. And these two different states of matter can be also used in different applications. Yeah, when we're looking to transport, we need a higher energy density, therefore a solid, will be more efficient. And when we're looking to decentralized application solution, it's the way to go, because there the efficiency is way higher. So when we need a high efficiency, especially in storage application for stationary application, then we will take it in solution. And when we need to transport it, we will crystallize the salt out of the water. That is a energy inefficient process, but therefore we increase the energy density to make it transportable.
No, okay. You need to get rid of the water, and that's always energy intensive. But if we compare it to liquefying hydrogen, is that about the same? Or what would you think needs more energy?
Liquid hydrogen carrier or liquid hydrogen itself, it's way energy intensive than in our case. Because when we're looking to the unloaded salt itself, potassium bicarbonate, that is way easier to get out of the solution because the solubility is low. Therefore, we have only to cool it slightly, and then the potassium bicarbonate will participate. When we're looking to the formate salt, maybe a higher concentration of the solution is a proper solution. And when we're looking at this location for transportation, this is the area of high excess of energy. When we're looking to Middle East and we need heat to crystallize or to concentrate the solution, there the energy is available, and especially heat is available to concentrate the solution or to make it in a solid way.
So you can crystallize it actually from the solution instead of having to evaporate all the water.
Yeah, this is one option, right?
Interesting. I thought that you would have to evaporate all the water, like when you get the sodium chloride from sea water.
Yeah, no, this is the thermodynamically worst thing you can do to evaporate water.
That's already one good example for the shipping. The salt makes it much easier. And let's talk about another aspect is also the safety part. We have already touched a bit on that, but for example, when a farmer or whatever has a few wind turbines and solar panels and they cannot use all the hydrogen directly, they want to keep some for the winter, for example. How could they do that with your technology?
Then he order a flat bottom tank, a big flat bottom tank, put in our salt solution and connecting this flat bottom tank to our container, and within the container there is the chemical plant. And therefore you see the big advantage, because the flat bottom tank itself is state of the art, and the farmer can handle service on this flat bottom tank without any fear of getting him an issue with hydrogen. And within our container there's the only part where hydrogen occurs, and that is maintenance due to us or with our team.
So we can avoid big pressurized tanks, which are also sometimes a hazard.
Right. And we ensure that only the dangerous part is encapsulated within a certain container, that the farmer is not thinking, oh yeah, I would repair it, and that that is a big impact, because when the farmer hit itself due to any hydrogen that occurs, that will be bad news, and therefore the whole technology will have a problem when such a bad news
definitely
come to the world. We see it for Tesla. When the first Tesla cars burns, the stock prices of Tesla goes down, and this is a big problem for new technology when bad news occur due to any personnel that is injured.
Yeah, definitely. And the hydrogen economy is just scaling, so any big bad news like this would also not only have a problem for the companies involved, but also for the hydrogen economy at large, I think.
Right. And especially when we're looking to hydrogen and the risk analysis of hydrogen infrastructure, we see that most of the accidents occur within the storage infrastructure. So mainly 68% of these occurring in the part of the storage process.
Oh, okay.
And therefore, it's not only a nice to have, it's a real world problem within the hydrogen infrastructure that when an accident occurs, it's often explosion or fire or both.
Oh, okay. That was new to me. That is a lot of this is happening in the infrastructure, not at the production or usage sites. Then it's even better than to have a safe technology in that part where the most accidents could happen.
Yeah, right.
That sounds great. And you already talked about scaling your technology. What are you currently working on to better scale this technology?
Yeah, right now we're working on a containerized solution of our plant. So we're starting with a small lab plant to show it that it works. And now we scale it up to containerized. And there we're focusing on get a certification on this container that is a real product, to go to the market and tell our customer, we have a product, this is CE certified, you can buy it as a plant and connect it with your flat bottom tank and store hydrogen in a safe manner. This is right now our goal, and we have a small team that take part of the whole different parts of the technology, from the catalyst development over basic engineering of new processes to detailed engineering of the container with all the piping and automation and so on. So we have a small team of engineers that take part on the whole value chain.
So can I imagine that like these standardized shipping containers, or what kind?
Yeah, it's a 40-foot container, and we cut it with in two parts. The first part is a 30-foot container, and the second part is 10-foot container. And within the 10-foot container, we have all the electrical stuff, and the 30-foot container are the apparatus to get the hydrogen in and out of the system.
Wow.
And then we can ship this container park to our customers.
And then would the approach be to just have multiple containers if you scale the plant, or would you then have a new concept which has a bigger plant in general?
No, then we will scale up our reactor and the whole plant itself.
Okay. Because
numbering up it's a good way, but only in a certain size. And from that on, you need to scale up the reactor itself, and with a fixed bed reactor that is easy to scale it up.
Yeah, because I was thinking a bit about the electrolyzers, and there it's a common way also until a certain extent, but still there's a lot of these containerized solutions where you just put more of them next to each other.
Yeah, right. And this is our next, after we finish the container, our next goal is to build a megawatt plant, and with this megawatt plant of hydrogen release and storage, we will have a bigger reactor. So we're talking about 4 to 5, 6 cubic meters to build this plant. Cubic meters for the reactor, for the catalyst packaging.
Oh, okay. So you said 1 megawatt of storage in and out capacity, or?
Yeah, that is roughly at this time 1 cubic meter to 2 cubic meter of the catalyst packaging.
Yeah.
But we see that our customers will prefer 3 to 4 megawatt plants.
Or for really large scale, I mean, the electrolyzers are slowly getting bigger and bigger, but that's also still in the process of scaling. And then it's more like 200.
And we are able to scale with the market in different sizes. So when the first megawatt project will be evolved, or 100 megawatt or 1 gigawatt. When we're talking about the big hydrogen transport, we are looking forward to scale our technology to this scale.
One metric is the amount of hydrogen you can take in and out, but the other one would be how much hydrogen you can store in one place. And that's kind of decoupled from your reactor, is it?
Right. And that is the cool thing about our technology, because we can decouple the capacity from the release power. Yeah. When we're looking to a battery, that is coupled. Yeah. When you want to have double the capacity, you have to double the cells itself. And with our system, we can build a reactor that is able to produce a certain amount of hydrogen, and the customer itself can choose if the float bottom tank has 200 cubic meters, 1000 cubic meters, or if he want to store even more.
Interesting. So this seasonal storage, for in summer you have a lot of photovoltaics, produce a lot of hydrogen, or use the electricity directly, but then you can use your invention to basically store a lot, but you don't need to get it all out in one step.
No. So you can charge it or discharge it when you want. So we can easily switch the process, and then you charge or discharge, and then you can only discharge 10% of your hydrogen battery, I would say, and then start again. So that is not the problem. And then we have to make a simulation with every customer how big the tank should be, due to the demand profile of the customer and the injection profile of the customer. And then we scale the reactor and the tank differently, precisely on the demand that the customer had.
So you also help them to choose what kind of size of reactor and tank they would need, depending on their energy profile.
Right. And there we looking forward to different energy profiles. Yeah, when you're looking to maybe steel manufacturer, they have a completely different profile, namely continuously in contrast to any village or something like that. Yeah, there you have seasonal effects or day-to-day effects, and then that is a different profile with a different system in the background.
Yeah, probably also a lot of optimization possible there with all these new KI technologies.
Right. With all the new technologies in regard to artificial intelligence in system design, it's a big advantage, and also in catalyst research. Yeah.
How?
Because heterogeneous catalysis is mainly trial and error, and when we can have a likelier solution due to artificial intelligence, our trial and error process is way more efficient.
Oh, interesting. So are you using these kind of computer supported research applications for your catalyst research?
Yeah, we're starting to include it in our research, because we see the advantages, and also in the whole AI community, we start to now develop technology or a workflow where we can integrate it in our labs to have a sufficient way to get to the goal.
Yeah, I imagine there's also great to be at the LICAT, which is good at all this catalysis research. I've been there for months during my PhD, and it was really impressive to see what all instrumentation and all their expertise in catalysis.
Yeah, and sitting at the Leibniz Institute for Catalysis is one of the biggest opportunities to get in touch with all the new inventions and with all the different possibilities in catalyst research. Therefore, we're looking forward to working together in the future to enhance our speed of development.
What is, in your opinion, now the biggest challenge that you're facing to bring your technology to the market?
Right now, the biggest challenge is the market itself, because hydrogen is evolving very, very slow.
Yeah.
And this is the big problem, especially for startups, yeah, because the time of your invention matters most.
Yeah.
And right now we're seeing Trump going to the UN and saying climate change is a hoax. That is not a good.
Yeah.
That are not the good place to be for climate startups right now.
Yeah, it's this hydrogen hype, I would say, is a bit over. But on many conferences, there were also people saying, okay, now we get into this realism phase where we can actually get to work and don't have all this blinding lights and prophecies going on that say we use hydrogen for everything and everywhere. And now it's getting more realistic in the use cases, which technologies really need hydrogen, where maybe we should directly electrify and such. So I think it's not over, but it's getting more realistic and you can plan better.
Yeah, and we see that we will need hydrogen in certain application, especially to decarbonize steel manufacturing or something like that. We need hydrogen to be the molecule of the future.
Yeah.
So we think that hydrogen will take a part of the world in the future, but right now it's hard times.
Yeah, but one of the biggest challenge where there's basically no way around hydrogen is the seasonal storage of electricity, that we need to take our wind and solar energy from the summer to the winter where we need it for heat and such. And I think that's where storage technologies like yours are really important and could really help Germany or other countries to keep most of their electricity that they otherwise would not use.
Yeah, right. And when we especially looking to the cost, lithium ion battery are way expensive in contrast to our salt. So they are 10 times more cost with lithium ion batteries in contrast to our technology. Therefore, it's also a big cost differences when we want to store hydrogen or energy in the long term.
Yeah. And it's also when you can use energy that otherwise would just be not gained. For example, when you turn off, lacking the right word here, but turn off the wind turbine, then it's energy that otherwise would just be wasted, right? And then it's not really...
Yeah.
The efficiency still plays a role, but it's not that great of a deal.
Right. In the H2 Apex company, I give a crash course about hydrogen, and there I always talk about my grandma and their cherry tree. And I say, okay, my grandma has a cherry tree, and she wants that I eat her cherries all the time. Yeah, in the winter, in the summer, or in my home, or in her location. And what she do? She get the cherries, put it on her kitchen and turn on the heating plate at full power. Yeah, my grandma doesn't take any efficiency into account. And that shows when we have such a substance like the cherries or renewable energy that are fluctuating in time or on location, we need to store it, and therefore we take into part that will cost energy.
Yeah, that's a great example.
Concentrate it in time and location.
Yeah, that's a great example. And what I also think is really interesting is that you started with your startup and to bring this new technology, a completely new approach. So it's not like some other big players are already in this, as I think, and that's really inspiring also for scientists to bring their technology to the market. When you started with your startup, what made you think, oh, maybe we should bring this to the market on our own?
Yeah, especially the low toxicity. So when you have it in your hand and you see, okay, that I can give my grandma and she can take part of the energy transition. That was my aha moment on this part, that our solution is able to hand over to a normal person. And that is the part that I imagine of a future where we can take part as normal human beings in the energy transition.
Yeah, that's a very interesting point. And maybe do you have some tips for other researchers when they want to bring their research to application, what they should do?
Yeah, try to get in contact with different customers or person that need that technology to test if your approach is good or not. So you can only test it when you go out and talk with people, interact with customers. Then you find out, okay, is there a market? Is the technology good or not? When you're only sitting in your chamber and think about it, that is cool, but nevertheless you cannot see the whole picture. And when you go out and simply test your invention, then you see the feedback of the person.
Definitely. We need to get into the doing and not just the theory part where we could do all this. It's just actually trying stuff and then see if people would respond.
Right. And yeah, from technology side, you will always have the best approach, the best catalyst and the best apparatus and so on. But we do not take into account that we have to go to the market. Yeah, we need a customer. And then we can further improve our technology, our catalyst, and so on. But we have to go in the market. Otherwise, the big industry with all and so will to start continue with their technologies.
Yeah. And when should you do this, contacting people? In what stage of the research?
I think at the earliest stage of the research, because you often get some insights. We ourselves started with homogeneous catalysis. And then you figured out, okay, yeah, we have some problems with the catalyst because it's in the solution. You cannot separate it from the solution, and therefore it's all. Yeah, and you cannot stop the reaction when you want to transport the media itself because the catalyst is inside. And then at the earliest point of technology decisions that you should do, then you have the interaction and find out, okay, you need a system where you can easily transport the media without the catalyst. Then you take the decision, okay, you have to choose another technology approach to do that. Therefore, I think to interact as soon as possible, prevent doing false decision in the technology process.
And also, I think interdisciplinary work is important, that the chemists should talk to engineers like you who probably spot problems that chemists just don't think about because it's not in their studies. And then
or to economics, because at the end it's all about economics.
Yeah, very important point.
You have to invent something that is cost efficient, and the economics, the economics itself, they do not understand your technology in all the different details, and that doesn't matter because they are focusing on how you get it on the market, in the market, and so on, and then you can readapt your technology due to the different barriers economic wise.
Yeah, definitely. And then you need to learn how to communicate all your technical stuff to other people who are not that much into the technical stuff.
Right.
That's probably also what your job is in your company, right?
Right, to have a team to push the team to new levels and also to explain the technology to others and to get interaction with different person to get new ideas to further develop our technology.
Yeah, great. Then I think we can come to an end of this discussion with my closing question. That is, what is your favorite discovery in chemistry?
Yeah, my favorite discovery in chemistry is about material science. Mm-hmm. Yeah, you know the light bulb from Edison, and when we're looking to the approach how he get the best light bulb for that is working properly over a long time, he has a trial and error approach with thousands of experiments, and that show that invention is not a thing that comes or sometimes comes out of the box, but sometimes need over long time doing the same stuff and testing a lot of materials. And in this time of Edison, there was no material science. Yeah. Yes, basically trial and error, different substances to get a light bulb that is able to run in a proper size and in a proper duration. Yeah. And also for our system right now, heterogeneous catalysis is mainly trial and error. Therefore, we have also testing thousands of different recipes to find out the best recipe of the catalyst to get our reactor running and have a good lifetime of it. So I see many parallels to that. Therefore, I like it.
Yeah, definitely. That's a great invention, and more about the process, I think.
Yeah, the process of invention, because as a scientist, you always dream about, you come to the lab and from a magical spark, you see the invention.
Yeah, but that's not the case usually.
in sometimes it's not the case. It's getting up every day and testing new recipes and new experiments.
And then you might end up with some new great technologies like your salts for hydrogen storage. Yeah, so
right.
Thank you very much for this really interesting talk. And then I'm looking forward to seeing your technology develop. Thank you very much.
Thanks to you. And have nice speakers in the upcoming podcast.
Also, thank you very much for listening. Don't forget to hit the follow button on wherever you're listening to not miss the next episodes. This also helps me to reach more chemists and spread all these super interesting innovations. If you want to talk about your research in the podcast, send me an email to contact@innovateandreact.com or connect with me on LinkedIn. Until next time, keep innovating and stay curious.